We'll now have Mr. Joaquim Luis doing a presentation about Earth observation mapping and exploring with GMT.jl. Joaquim Luis obtained his PhD in geophysics in 1996, IPGP, France. He's currently an auxiliary professor at the University of Algarve. His research interests include marine geophysics, namely North Atlantic marine magnetic compilation, plate cinematics, tsunami modeling, and scientific programming writing and development of visualization tools. He is a core developer of the generic mapping tool since 2008, co-author of the GMT MATLAB interface, and Swing, a tsunami modeling tool in C. He is also the author of the Myron, that is a MATLAB GMT GUI for Windows, and the JuliaGMT.jl and Remotes S.jl packages. Thank you, Joaquim.
Oops, no.
Usa o adaptador. Vamos ligar aqui.
Vamos fazer deste não. Deste não. Aí, não.
Aqui. Agora liga aqui no teu.
Aqui, deste lado.
Lado?
É.
Já está.
So, hello all, good morning, especially for the ones that are not here. So, I'm going to present, I've been watching and participating on the Julia community for a long time, but this is actually the first time that I will present what I've been working for in Julia, which is this wrapper to the GMT tool. GMT, for those that you do not know, is a very well known in this, especially in the geophysics community, for a long time. It actually started at the end of the 80s, but by the time to PhD students that named it GMT after the gravity, magnetics, and topography, because that's the things they were studying, and at that time there were no tools for making maps, nothing. So they started with that and later changed the acronym to mean generic mapping tools and make a point to make it generic all the time. But the figure that we are seeing here was produced in 1991 with a PostScript that started at that time. And they were able to make that plot, which now seems trivial, but I repeat, it was made in 1991. It made the cover of, some of you might know, the HGU journal EOS. So that's when I learned about GMT. I was doing my PhD at the time, and I only knew a bit of Fortran, and then I needed to drop some magnetic anomalies on top of topography, and GMT did not do it. And well, I was stubborn enough to learn a little bit of C, and was able, without really knowing how, to make that dropping at that time. And that's how I got involved in GMT, you see. And a little later comes the Myron thing, which is a MATLAB GUI, that because with students I tried to teach them GMT, and I was not successful. Oh, no, okay. In the Google Drive you have two notebooks, or two versions of the same notebook. One empty, and the other one that you can run. But because there are some issues in the middle, I already run all the cells to not have any troubles in here. So that's what I'm going. So you have both. You can just follow from the screen or execute them. GMT has very little direct dependencies. One of the reasons he has very little dependencies is because GMT itself, the library, already have most of those dependencies included. So since I think 2008 or something, GDAL was included in GMT. So when you install GMT, either the Julia wrapper, via the Julia wrapper or the library, you already get all of those. That dependencies that gives access to read almost those formats, the raster and vector. So most of the things, I don't need to include more extra dependencies here, Julia, because they are already accessible. But start with, I don't need to increase the font That's not the point. This is the example on modern GMT, what you have to type, to write to make that figure that I just showed. So GMT is very, and with the time there's options to do everything. But it's very condensed. So you do an option normally with a single letter. And you have to type things like, if you see -n, -c, -p, -r, this is all the instructions to do the commands. Well, you work it well for many years, and for people that learn GMT this way. But in modern times, people are not really more available to learn this type of language. So I started because of the two things. The other GUI from MATLAB, I wanted to port it to Julia. That's what the main reason I started with Julia. I'm still waiting for deciding what the graphical thing. It's a bit of the same purpose as now I forgot the name because that he asked it for the HDF viewer. Is this a bit of the same thing that I also want to do with that one? But meanwhile, and also because I think people in GMT core users could profit a lot of using this way of making the same maps and processing in GMT, I developed for a long time the Julia wrapper. Julia has a couple of 3 or 4 types, which are simple types. Grids, images, datasets, polar maps, and one that's used but not by the users is the PostScript. The types, which are they are described here, are simple types. They are either matrices, well, they are always matrices. It's either a grid or an image or a table. They are matrices of the same type. And then you have other fields for method. So you can have georeferencing and other type of information in those types. And those types derived from the previous work that was done to a MATLAB-based toolbox in which you can communicate directly memory from the data to MATLAB memory and back. And that thing was sufficiently close to what Julia does that I could port it more or less one-to-one, although with a lot of work, to Julia. So we communicate directly from in memory without writing temporary files. And the GMT-C code has certain internal types that are mimicked by this one. So that's why they are the way they are. We have a type for a grid, a type for an image. In MATLAB, in GMT, we distinguish between grids and images. Images have colors, grids have whatever information, temperature, the bathymetry. So internally, the distinguish is made. And then I extended a bit some of them, the data sets that added attributes via dictionaries and things like that, and then georeferencing. But it's a more limited type that you get, for example, for data frames, which are also supported via weak dependencies. But you can have attributes, you can have all the referencing, you have the geometries, you have all of those things with the limitation that they all have to have the same data type. I cannot have integers and floating points in the same type. So in that regard is a limitation for broader use, but for GMT internally it is not. So a couple of examples. The grid type, and well, those types, they use the array, it's written here, the abstract array interface. So it means I can simply, with a grid, do operations like this one, small. Say I have a grid, I want to calculate another grid, I have 1 to 2 times the other. So it's just not only do the same operation with the matrix, which is trivial, but you also have to update the metadata that comes with minimum, maximum that is used later. So, but for the user, the only thing you do is you do these algebraic operations with grids or image as you would do with any matrix, and the internal machinery of the types takes care of updating the things that need to be done. Okay, another thing, figures here in this notebook are large in this on others, because another thing of the particularity of the GMT, it produces PostScript. And it works in a layer cake model. So You have one layer with one thing, and you keep adding things to that image file, whatever. So it means you can do a lot of very detailed things, and you put them on top of the others. But that means it's not interactive. So this is you produce, call it static images. It's not interactive. For example, one consequence: you have to define our domain, our limits of our image on the first call, because you cannot come later and say, okay, but this data set is larger, let it automatically expand the axis limits. It does not work like that. I have first to know what is the limits and then create it. And the other thing is the plots in GMT, which are produced PostScript, that later GoScript converts the other raster formats, GeoTIFF as well. The units are centimeters or inches. It's not points. So you define the size of a figure with centimeters, and you can go up to 11 meters. If you want to make a figure with 11 meters, you can do a figure with 11 meters. Coming back to this, I am not able to make smaller figures in the notebooks. It decided to have the largest, the width of the screen, and the figures are a bit too big. I would make it smaller, would be nicer, but I have no control on this side because it's the Jupyter that decides to make them like this, and I never found a way. When I have images with pixels, I can say with 50% or something like that, and it obeys. Here it does not. So this figure by default is 15 centimeters, can make it as small or as big as you want. When you make them small, those who have experience, you know that then the labels start to coalesce. There is internal algorithms to try to guess the size of the text that still do not overlap, but if you make it very small, it's impossible. So this is an example. Oh, another thing that's my preferred taste for users, I try to make simple figures possible to be done with a single line. So I made many gymnastics, for example, in this one, that is the peaks function that people use MATLAB know about it. This is the same one. And then you make an image. I have the color bar, and I have the contour, default things. So the contour, for example, I could set the thickness of the contour lines, the ones that are annotated, the font of the annotations, the colors, the left, all of that. But to do that, you have to use the function contour that gives access to it. But because most of the times what you want is just a quick and nice one, you have those versions as well. So this could be much more elaborated, but would not, of course, take only one line. If I want to make it 3D, it's 3D in perspective. The GMT is not 3D, it's not volumes. So you cannot do a volume figure. But you can take a surface and make it in perspective, like this one. And again, I try to make it simple. Let's say the viewpoint, and automatically has a default height, which is 6 centimeters or something like that. Again, you can change all of this. But using the defaults allows us to say, okay, I want to see the perspective from, this is azimuth. So under 35 means under 35 degrees from north is an azimuth, is not a mathematical angle. And you get figures like this. Also, shading is a very useful operation that when you want to look at data, because when you do non-shaded images, things look good, but if you have noise or other troubles in the data, the shading is a very powerful operation to show it. So I got the habit of using that almost all the times. Images as well. You load an image and plot it. This is just a JPEG image that comes with the tests, so it's reproducible because it's on the test data set. I got that one for the next figure. Found it in the internet somewhere, because you can also plot them in the sides of the cube. This is a half finished work, because my real intention is to be able that instead of having the top one, having a surface, the surface will go, will not be flat, and I want that the figures on the sides of the cube would follow that surface, and it means in this case I would have to clip it, the gray areas. But okay, if you want to plot them in the sides of a cube, it's also, this is already kind of an extension. It's all done by GMT, but the commands that would have been necessary to do all of that would be a lot longer than just this one. You say qplot, you give the 3 images, and by default, it does that. If you want to just put some of them, it's also possible, but you have to consult the manual as normal. Vector data. Again, as I said, because GDAL is already a dependency of GMT for many years, can read the vector data, OGR vector data directly. So most of them is concentrated, I would say, in this GMT read function. That reads images, vector, whatever. It decides that by the extension when it can. Otherwise, there are keywords that you can add to help it. It's a grid, it's an image, it's an OGR, whatever. So the most common ones are detected automatically, can even be zipped. And if you load this one, this example is something I saw from, I think from a tutorial from R or something doing some data science in Colombia. And well, I decided to try to see how I would do it with the GMT. And okay, it's this. Just read the Colombia shapefiles. It plots. The show method shows some information of the data set that we get when we read it. You have the geometries, you have the projection, the referencing information, shows some of them. And, okay, again, there is one image. We also have a viz function because I'm also a bit lazy. The less I can type and it's still readable. And so I think it was Julia that first came, at least that I saw a viz function. And sorry, I hope I pirated also. You can say EM show like you do with MATLAB. You can say viz, you can say others. But this one is really short and it is nice for this. So, and this is quite a bit for what MATLAB does is projection. This case does not require that much because, as you see, we are at 8 degrees of latitude. So at close to the equator, you don't have much deformation. But when we go up, when you go to Greenland, if you don't do projections, you get a very deformed image. So projections, when you do maps, is something I think should be present all the time. This one here, when you say proj, well, proj equals guess, it means because it knows the region, it knows the referencing system, it can go at least directly from geographic for the other ones, and it decided the projection that he used. Probably use it Mercator because it's close to the equator, but he uses different projections, we'll see, for other regions. So this is a projected map of that shapefile. I'll stop the examples here. We can filter with the filter. I overloaded the filter function in Julia, and you can select the name of one of the departments here. In this case, you say a filter name equal Antioquia, and you get the polygon that contains only that department, and you can paint it with. It's the in Julia and the other ones. This was more or less the common names. You have the fill for the color. Well, you have title and again the projection, and you get things like that. So, briefly, there are a lot of drivers in GDAL. The list you see here is the list that you get from the Windows installation. It's very close of what you get from the artifacts that you get from Julia. Because the number of drivers are almost the same. Perhaps a bit higher in Windows because I build this frequently and I use a lot of drivers. But say you can have the list of all the drivers you can have for the rasters. That is not an exhaustive list. Alexander mentioned ZAR. I never use it, but it's here. Many of those things I never tested. So, like it happened yesterday with this, I will try to load complex array through this. I got an error that probably was because of that is not accounted. So in several of them, for sure, if you try that, at least ones that I did not test, it's very difficult to put tests for all of those things. You need files, examples. So, yeah, sure.
just curious, like when you send that projection keyword to the vis guess, what is the heuristic that you use in order to guess the projection?
I saw what happens.
Okay.
And I can show you, there is a function that's called proj guess or something, more or less that's the name. And depending on the latitudinal extent, it selects between 3 or 4.
Oh,
so
got
that's
it.
Lower latitudes, traditionally, especially in marine things, we all use Mercator. And we use Mercator even when we should not use Mercator. So traditional, I keep using Mercator in Greenland, which is not a good case, because the deformation of Mercator grows a lot when you go up to 50 degrees is still a little bit, but manageable. But when you go to a very high latitudes, then the deformation is very high. So there is a function with 3 or 4 that looks splendid because this is especially by latitude.
Yeah.
So there are 3 or 4 projections that it pre-selects and it generates the proj string of that projection applies them.
Got it. Makes those things.
If you want to make a global map, you will do this. There are many. Maybe I will do a projection. If I want to use a Mulwave projection, I would spell it like this. Set the color. GMT comes with its own database for coastlines. It's a very detailed one, old, detailed, and old pays in one thing. Because it was made in the 70s, last century, it uses a different data. So if you scale down sufficiently to see the difference and compare with satellite, you will see an offset of about 300 meters something. So if you go to that scale, you see that. But otherwise, you have this. And because it was done at the time that the computers were, we don't imagine how, those 90 megabytes of netcdf files were compressed, made in 2 integers and 2 bins and 2 scale. So this could be done 30 years ago with the same resolution, and you can do that. So these are not polygons. These ones are line segments that are joined and filled. And there are several tools to compute masks, many tools that use this database. There is another one which are polygons that came from the DCW digital chart of the world polygons. That it's an alternative, and those are polygons with the countries. What comes next? So it also has states from the biggest countries, rivers, maritime boundaries. This is an example of plotting the Americas, north and south and center, with the countries, the states, and this blue is the maritime boundaries. I don't know from, it's probably, no, not Hawaii, no, south, don't know of one of them. Not very interesting from here. If you want to do a Lambert equal area projection, do it like that. More, okay, more thing. Another thing that GMT uses, a lot of them use the physics. So the GMT servers, sorry, it's only one. No, that's not true at all. I even have one in my university. Does not have all, but you have other servers have copies of the same data. Have a collection of, not so extent, but perhaps I have to swap a little bit. Data sets with these things. You have the seafloor age. You have the GEOI, oh, it happened yesterday. I don't know why. Huh? Okay. Mean sea level, several, the ETOPO, SCRTM. We have SCRTM up to 30 meters. Because these are very big files, SCRTM for the whole world at 30 meters is 45 gigabytes. The server have those files tiled depending on the resolution, and we can ask to download them directly. This is what you can do if you run the notebook, but well, it might not take that long because it's a bit like we were saying from the netcdf, and you define the limit, you only download the bit that interests you. You can have those are pre-prepared, were filtered with very good filter that when it filters by distance, it knows that it's filtering a geographical quantity. So when you go up north, your filter has to extend east-west because the degree of longitude and latitude will not cover the same distance. So these type of things are very detailed and well implemented for a long time. And those data sets are filtered at different resolutions. If I ask, for example, again, I say the gas, shade, first I downloaded this one. And they have a naming, which is simple, Earth relief. One is for Earth, for the other planets is other names, and then the resolution key. This one, 05M means 5 minutes of light. You can go even to the seconds, depend on the data set. For the Earth, you can go at 1 second, which is 33 meters. Of course, for that one, you are not interested in doing anything larger because you will wait a long time for the download. So if I do this here, GRD cut, well, it's a GRD cut, the name of the data set, and a named region. Each one is IH023. Hydrographic Institute has named regions, and you can also call, instead of giving, you could give a limit in geographic longitude and latitudes, or using named regions. I use a named region to download this one. So see, the command is GRD cut because it will cut from the global one, these limits, and creates a grid type, and I only have to say again, show me the picture with the grid type, add shading because it looks good, and in this case I did not add anything more. So, and you get the map like this. Next one thing is the Azores, where you see the quality of data is of course no longer so good, but that's what's publicly available for the bathymetry or audio source. This one is the same thing, except that I use a smaller limit around the islands, and I added the coastlines painted, so to help us localize better. It doesn't. Oh, another one. You can also use the facility that we are nowadays that when the data is publicly available, for example, to make seismicity maps. There's a function that's called seismicity that by default gets the last month of the seismicity as provided by the USGS. You can tell this, you can control this by magnitude, by date, period, can be a week, can be a year, can be many things. The default is 1 month. At the end, this is a legend. Legends and GMT are very detailed. Not so easy to do. The default ones, yes, but if you want to do something very specific, you have to read the manual of the legend command that allows to do things. This is a legend. You could put this a legend in other plots. In XY plots, you can put also legend easily just by saying legend equals yes or something like that. You get the defaults. When the defaults are not good enough, then you have to go to the model that does the legend, and that one is not so easy, so simple to use at the first sight. So you can do things like that. And this is very recent because GMT 6.5 was released officially, I think, Monday. We don't release that much, and it takes time, and then last minute bugs are always delaying. And while it was not released, the other planets were not available. Now they are available, and instead of asking for Earth, I can ask for Mars, and I added the coastline of Earth on Mars so as to help us localize, and the Mount Olympus would be here. Well, see, you have the US coastline to help us. So you can do Mars, Jupiter, no, of course, Mercury, Venus, Moon, and Pluto. Pluto is out. No, Pluto is not complete. Pluto is only this. The satellite that passes there did not cover the entire surface of Pluto. See, Pluto is only this. But you have here Moon, Venus, Mercury, Mars, magnetic anomalies, global magnetic anomalies, and well, the collection is not larger than this. But these ones are provided by GMT, tiled, and very handy when you need it, especially the bathymetries and topographies. So, again, if you want to see it in perspective, you do the same thing, which is nicer than the first example. Then you first see, you set an elevation, azimuth and elevation, and you give it, well, that and say shade. Again, I cannot plot so easily the coastlines on here. I would have to do more operations because it's perspective. I would have to get the coastline, interpolate the grid to get the Z, and then I could plot that line on top of topography. But if the line only has 2 dimensions, I cannot plot it on top of the surface automatically. well, I can write something that under the hood does the operations, but that's what would have been necessary to do in order to put the coastline in a perspective view. Oh, I talked at the coffee break with Simon. I also may have a mosaic function that does what MapTiler, similar to MapTiler. It's not a duplication of efforts. I had that in 2018 MATLAB. And it was not ported. It's a code that at that time downloaded Google Maps, not Google Image, what we now see in Google, and Bing. The problem with the Google is, by their terms of use, we cannot use them, even if you know how to use them. But Bing does not have that restriction. So by default, what this mosaic does is to use the Bing service to download the images, which are, depending on the zooming level, is satellite data or aerial photograph. One is high resolution, is never satellite data, it's always aerial photographs, which, by the way, are provided by the countries, free to them, and then they have terms of usage that say that you cannot use them. Well, fortunately, Bing, from what I read, did not have that restriction. But to use them, you need to tell it where you want to have the things. Again, Udal came to the rescue because he has access to free server that gives us geocoder. So, because normally you have to have an account, have a key, and to ask for a geocoder. Udal has two. I only tried it once. So that's what I use in this. Where is it? Geocoder function. Yeah, is where? Yeah, geocoder. What did I put? Well, the address of the hotel call. I'm going to do heroism. I had to help it a little bit because my first attempt, I landed on the north side of the island. Apparently, there's another caracol there. And so I have to be a bit more specific on the address to get here. So I typed the address. I got the geolocation of and then the next thing is to tell it, mosaic, give me the image. There are more than one ways of using it. Also, you know, this images came in tiles of 256 by 256, and the resolution depends on the zoom level. So either you give it the limits, and it finds the resolution, or you give 1 point and say the number of tiles around. That's what I did. After some attempts, I said 7 neighbors is enough at zoom level of 19, and we get the best that Bing can give us at this hotel. I can tell you, Google does better. Not does better. The images in Google are 1 or 2 level higher than this. Can do the same for the island. Just say, this one I can say Terceira, just an MOO, to get the bounding box for the limits of the island, and you do the can project this image. They are projected. Oh, are they projected? Yeah. Yeah, project, yes, they are projected. So, because they are referenced, we can use the projection machinery easily. You can specify the projection you want. I normally use the guess because what it gets is normally good. But if you want another one, you have to give the parameters of the projection to it. Also use is tile provider. So you can use tile provider. Tile provider has a lot more, is a significant number of providers of mapping tiles options. So if you use tile provider, you can use the output of the tile provider, the type of the tile provider, and use it to make those images through mosaic. It's not particularly good, but I did not want to use the default, fortunately, because Simon also used it when the default is the night, day and night. That's what I get by default. I searched it. Another one is meteorological information. You have lots of. This one is really. You have to consult the MapTiler manual because you have really a lot of options to do these things you can get. You also can easily OpenStreetMap is straight almost for the mosaic, but these ones that have a lot of them requires more work from the user. Okay. Time. Oof. Another package that's separate because you have different dependencies is for the remotes. I call it remote S for remote sensing. And I use example. Well, when I made the presentation, I did not know about the Google drive, so I have commented the things that you uncomment to download the data. But the data are Landsat 8 scene. Each band is about 80 meg or 90 megabytes, so it would take a lot to download. They are in the optional folder in the Google Drive. But there is also what is going to be used. You can with the for those that you don't know, the Landsat comes with what we call the scene. It's bands between 1 and 11. And all of those bands. You can download them all, or just some of them. And it has also a file with parameters for doing corrections. It's the MPL file that you also need to have it together. But it's a large, there are 200 kilometers by 200 kilometers, a 30 pixels resolution gives something relatively big. So you can't concentrate and say, I only want a chunk of that area, but you have to give it the limits and create a cube. That's what the commented part here does. Cut cube, say the list bands that you want, a template to not repeat that very long name of the files, and then save that in the GeoTIFF cube file georeference. That's what was done previously, and I load that cube. The report bands information gives the names of the bands, the wavelength, and so forth. And for example, you want to compute the temperature. The temperature come in digital, these come in digital numbers, you have to apply an equation. But some of the times it's just a straight line transform, other times yes, a bit more. Don't remember. This probably, but you have to transform that. That's what this dn to temperature does. So you give it the name of the cube, say the number of the band, and you get the temperature. I also added, this is the region of Lisbon. I use that for other things because along the Tagus River there are agriculture, and you can see very good examples of how the DVI and DVI index works well for this region. So that's why I like to use this region, especially because the river, the Tagus River makes that. But this is the temperature. I digitized 4 points here. I have to resample. I use a GMT model to do that. The resamples use the accumulated distance along the track. So you create the track, and then you can, there is another model that called GRD track, that you give it the track, XY positions, it reads the grid, and interpolates along those points. The shape of the line can have any shape we want. And if you do this, and you get this profile, temperature versus accumulated distance along the track. Not mentioned. Those two spikes are not outliers. Lisbon people, what they are, you can guess?
It's the bridges?
At the bridges, exactly. You can see them. You can see. If you come back, you see. There is the older one, and the narrow part of the view is the old one is a narrow bridge. It's the one that is looked like the San Francisco monsoon. And the newer one is longer and has more length, so it's larger. And you can see the difference in temperature between the asphalt and the water that is below is sufficiently clear that you see them. So this is not, they are not outliers, are the temperature when we cross over the bridges. Using that cube, you can make easily, when there are not many clouds, a true color image. You just say, I have the cube, it has all the information that it needs, it's stored the information from the MTL file with the parameters to do all those informations. It's stored as metadata of that GeoTIFF file. So if I want to do a true color image, I just say true color and the name, and I get this. This is one that works well. Sometimes it might, because it's automatic, that's the point. And I'm going to show what is done actually. You can calculate also what is called the radiance on the top of the atmosphere by a transformation that you can do with the parameters that come with the scene of the Landsat. And if you do that, for example, this one is for the blue, yeah, the anti-radiance band name blue, so it's for the blue band, and you plot it, you get this. I still see a little better. If you are looking here, you see very dark. You see almost nothing. Why does that happen? For those of you that know how these things work, data is acquired with 16 bits. And you have 65,500 something possible digital numbers, which are not all used, by the way. The clouds are more in one of the sides, but most of that interval is still not used. And when you do automatic conversion for an image, you have to compress that integer 2 to integer 1. So it means from 65,000 something to 256. So if most of that is not used, you will have only the lower numbers, and then you get a very dark image. So you lose your dynamic of your data like that if you do it. If you just do it raw, you get an image. It's very dark, almost black. So what you have to do is to find what is the interval where data lives, and then take only that interval and stretch that interval. Not stretch. So we say contrast stretch, but you say in fact when you reduce it to the 0 to 156 interval, you only use that where we have data. Well, this is a nice behaved one because sometimes when you have clouds, you might have spikes, and the automatic thing might not work. In that case, you would have to use the histogram model with the numbers that you manually would have to give it to make it work. But when things work well, what it does, it takes this and automatically, if I stretch histogram, now I have this. It's the same one, but now we can see. Just one band, so it's preferably to show it on grayscale, but this is the blue band. And what the true color does is it does automatically these 2 3 bands. It can compute a true color image. And I don't know if you can see the difference. If I put the raw and the radiance on top of the atmosphere side by side, can you tell the difference, anyone, between the two of them? It's not big, but I think I can.
Okay.
That one's sharper, that one's better. Yeah. So it's worth doing the atmospheric correction. It does not take much, but this on the left side is the raw digital numbers, and the other one is doing the same thing, but using the radius in top of the atmosphere. In fact, there is even the reflectance of the surface. You can have models to compensate more elaborate things to do for compensating the effect of the atmosphere that supposedly work better, and it's not difficult to implement. I will do it at one point, but I have no need so far. Can also compute the NDVI. NDVI is very popular index to find green vegetation in green state. It relies on the behavior of vegetation between the red and the infrared. If the vegetation has water, it reflects a lot in the infrared, and it does not reflect on the red. So based on that, they have been invented many indexes, invented because there's no theory behind that. It's really attempts, trials, and people have done that. Where is it? NDVI is NDVI is simply infrared minus red divided by infrared plus red. The N is from normalized is normalized vegetation index, difference vegetation index. And it has a particularity. If you take only the values above 0.4, more or less, you get the vegetation that is in the green state. So, because the equation is simple, Julie is just programming this, yeah?
Very interesting. The true color and the NDVI. So I see like how are the bands selected to say the tip is like a highly spectral images. Remember, a lot of red bands and like several red bands. Is there just some preset wavelength under the hood that they choose the band closest to, or?
It's made to be automatic in Landsat, which I use more, and the Sentinel. But you also can give the functions that calculate them, you also can give them manually the bands. So if you cannot recognize it by the description, which one, because for example, if you have several near infrareds, there are indices that do not use the red edge, they have the next ones. So that is not automatic. But you give it the band number and tell it to compute, but you say which are the bands that have to be used to compute that. So it's automatic up to one point, but the simplest case, and the other ones you have to know yourself what are the bands that you want to use, because you can extract the bands by name and you can do the calculation separately. You would just extract the bands and make your calculations in pure Julia.
Okay.
Because it's a abstract array, you do like it was done. So it should work. That's the idea. So when the defaults do not work, you tell it manually. The arguments they are options made for when they need human intervention.
Okay. And that would also enable to use a true color function to display some let's say infrared bands or something like that, or make different mappings of the bands to the colors easily.
You get not sure that I understood, because what you get is the image of. Okay.
Yeah.
If it is an image, you already have the colors. That's the point. But if it is something you calculate, you get a grid. And with the grid, you can put any color scale that you want.
Yeah.
I don't know if I'm answering your question or something else. Maybe not.
Maybe not completely, but I think I understand it.
Not completely understood. I would dare to say that yes, you can.
Okay.
But we have to see details. So this is the NDVI. If you just clip it for the 0 above 0.4, you get the vegetation. This is not the vegetation. It's locations where you have the vegetation. Yeah. You can turn it into a mask, say just different from 0 or equal to 0, and you get a mask with zeros and ones where you have information or not. You can apply it to the true color image. There is one step in here that should not be necessary anymore with 6.5 GMT, which is the transparency, but when I tried it, still needed, so I did. What that step is to save the file on disk and read it again, because it should be a transparent image that we are seeing. So apply alpha layer to the image. You have the RGB plus the alpha layer, so it should be a transparent image when you load it, for example, in another software. And this is good for what? Well, just to verifying that the NDVI worked well. Only thing that we got was green part of it. If we got any blue or red or something, it would mean that the method would have not worked well. In fact, this is with the raw numbers, with the radiance on top of the atmosphere, the results would be a bit better. I know, for example, this, I don't know if you see the mouse, this area in here is a park inside Lisbon, it's very green. You could have had a bit more of things, targets found, but I'm about to finish. What comes? Yeah, there was our paper of MATLAB, the thing that was in the root of the Julia wrapper, in the paper that we published. There was a long, I don't know, half a page of commands where you drape. Oh, did I jump anything? No? Maybe. No, I did not. Sorry, this remote S package also can read level 2 mode is data, which for those of you that know, come with the coordinates of the sensor, which means they have an array of numbers, and they have an array of longitudes, another array of latitudes, and the data is not equally spaced. Because at that reference system, the sensor, when it looks at the Navi, sees the highest resolution footstep, which is about 900 meters, but when it looks sideways, the outer beams see something like 4 kilometers. It's by design, because the Earth is a sphere, it cannot, it's not a flat, it cannot acquire the regular space. It acquires the grid cell increases more sideways in the area. So that's how they furnish the data, but that's the highest resolution that they can get. It's a level, well, there's also level 1, but it's still not. So it is for engineers to process and get us the data. So this model can read these and automatically fetch the longitude, the latitude, the numbers, does an interpolation, which for level 2 you will use. Well, we did it 2 kilometers, because it's midway between 1 kilometer and 4 kilometers. So it automatically read the level 2, now NetCDF, before it was HDF, and then NASA decided to change all of that. It wrote a lot of things, you know, they're all breaking all the time, because they decided, listen to me, Francisco, they decided to go from HDF to NetCDF, and they brought all things. But they have it there, you can read both, and you interpolate, because the interpolation is just near neighbor, because the points are close. You could use another more slower method, it would not make a big difference. You have the data comes with quality. Level 2 data, again, for those of you who know, most of the times have gaps because of the clouds. You have to try to find one with 50% data is already very good. So you have those averages, you need to have many of them. And this one, which took a long list of commands to produce, is a figure made with the SST on the, of course, and on the ocean, and on land you put the topography. The operations that need to be done to this is you have to take one of the grids, take a mask of the land mask, click the image from one, and do the opposite from the land side, and then you plot one on top of the other using the transparency. Well, in pure GMT, you still have to do it. In GMT.jl, I made a wrapper that's called Sealand. There is also another one called Terramar, and where you give it the parameters for the seaside, seas, GRD, the earth. Well, maybe that we cannot read. So I download the topography and put it on land, and I use the grid that was calculated from the L2 MODIS data, put them together with this single command, and then the other two commands is to have the color bars, one from the temperature and the other one from the altitude. I also applied shading, which is an operation that is more for DEMs, but sometimes it also works nicely for temperatures or other things, and that's how we see all these details, the curls in the Alboran Sea and in the south. By the way, I live there. And chlorophyll also makes very nice pictures sometimes. You can do the same thing with the chlorophyll concentration. And chlorophyll concentration, because it spans for several order magnitudes, you have to apply logarithmic color scales, otherwise you don't see nothing. But you also can make very pretty pictures like this. And see, to do this picture, well, adding some flowers, which is the rose, I forgot the name in English now, the Rosa dos Ventos, and things like that. Well, about finished. This is one layer. Oh, no, this is the last one. Still comes from the time of the other one, the Meron. I have a collection of 20 or 21 years of downloading the level 2 data for this region, calculating the weekly averages, monthly averages, yearly averages. Yes. I started with one and that did not care. There's too much noise, more noise than they say in the data. So I had it in 1 kilometer. It was too big for nothing. So I filter, I do 2 kilometers. The file it's there in the Google Drive. Yes, 19 years of that. So it's a cube of SST. I just showing one of the slices. Cube slice, I sliced the third layer of the cube, and again, like the others, I made the picture. And because I have this cube, I can also do things like, let's see how it behaves on the vertical. So it means along the time. When I made these, I did not add information about the time on the vertical. So that's what one of those lines here does. What is it? Yeah, this line here is, say, collect 2001 to 2019 is to have the years instead of having just the layer numbers. So we can have a nice plots. Normally, that's one thing that should have been done when the cube was created, but was not, so I added later. Because the grid type also accounts for the third dimension, and you can give it names, descriptions. Many times you have metadata that you can also put as metadata of that type. And the next two and final figures is, let's see what has been happening on temperature at one point, more or less around here in the Mediterranean, and another one here. I'll show it, please. So what I do, you take the cube and you look at the same cell along the 19 years, and you do the plot and do a linear fit to see what's the variation. And the first one is the point in the Mediterranean, where this is yearly averages temperatures. This is, oh yeah, now he comes back. Unfortunately, a bit too big, but this, you can see the numbers. The numbers are, again, it disappeared. Okay. Yeah. So the temperature at that point on the Mediterranean, the sea surface temperature at that point in the Mediterranean has been clearly increasing. But again, contrary to the people think, That does not happen everywhere. There are places where it increases. There are many places where the signal statistically is not really nor yes nor no, and some other places is decreasing. So this is an example where it's really decreasing. You see the parameters of the fit. It's 0.48 the slope of that straight line. So it means it's 0.48 degrees per year. Not much, but if you multiply by 20 years, you already get 0.9 degrees. So that point in the Mediterranean, on average, have increased 0.9 degrees.
This is annual means.
Annual means. Well, there are more clever ways I started to the seasoning, to do these things. I started by everything, and it's still on the list to be done to do it better. But only the simple operations of calculating yearly averages remove us the seasonal signal, and the results are not very different. If you do it with month, the result is much higher, many times. It's much wronger. It's a mistake that I keep seeing, I mean, even in papers. You should not do this when you have the seasonal signal on top of that, because having 1 point more or less on the two tips is sufficient to change slightly the value. So this is in the Mediterranean, but if you look on the upwelling area of the coast, the signal is contrary. Probably you know why. It's the wind, because it's been enforcing. The thing is, the temperature close offshore, the west coast, has in fact been decreasing with the time. Most of the places increases, or the signal is not convincing one way or the others. Some others are decreasing, but some, this is, and if you look at the signal with the chlorophyll, you also see a slight increase. So, yeah, there, this area? The Azores. I never look at the Azores because I use that area. I would like, but if I extend that area from what I showed you till the Azores, makes very big files, and I started to do this analysis with the MATLAB code, which is 32 bits, so I'm very limited on memory. I have to do a lot of gymnastics to be able to do this with only 32 bits, not 64. So I did not extend it to the Azores, and also because the files at the time were huge. But okay, I think it's my last one. This is not really very efficient because it's taking the slice entirely area when you doesn't need that. In terms of efficiency, what I should do is use what Alexander showed us with that, because it's also he showed us examples of doing similar things. So to continue this, probably the clever thing I should do is to use the work of Alexander, because he already done that type of things. I learned it 1 hour ago. Okay, and I finish here.